All right, in this video, we're recapping some of the stuff that we talked about last time on Power Series. And this video doesn't necessarily have any new material. However, I'm going to be phrasing things in a different way. We're going to be coming at it from a different direction. This idea of a Power Series is kind of a big idea. This is sort of an important concept to have nailed down. So I certainly recommend that you watch this. But that said, if you're really feeling good about Power Series and you've read section 9.5 and it all sounds good, then feel free to go ahead and skip this one. Okay, so up until this section, when we talked about a series, what we're talking about is taking this infinite list of numbers and adding them up. When we switched over to Power Series, all that we're really changing is rather than adding up just a list of numbers, we're adding up a bunch of different functions. And so I want to talk a little bit about what that looks like. So starting with sort of our basic example of what a power series looks, basic example of a power series. We're going to take the sum from n equals 1 to infinity of x to the n. All right, and so the start of that looks like 1 plus x squared. Oops. Different colors here. All right. The start of this looks like 1 plus x squared, and there are more terms. There are infinitely more terms, x cubed, x to the fourth, etc. But I want to start off by talking about those. All right, so if we were to graph this function, or graph these functions, we've got our 1, which is just a constant function, x, which is a line, and then x squared is a parabola. Got to pay a little bit of attention to where this goes. Okay, so we've got our functions here. And so I want to talk about a way of thinking about this power series. So whenever we add functions together, what that really means is we're saying for each of the x values, we're going to be adding together each of the functions evaluated at that x value. So put another way, when we're talking about x equals 0, what we're doing is with our whole series, what we're doing is we're adding up 0 plugged in for x. So 1 plus 0 plus 0 plus 0, etc. All right, and 1 plus a whole bunch of zeros ends up just being 1. So this series, this is a perfectly valid series, this series converges to 1. So when x equals 0, this thing gives us an answer. So we would say that this function is defined at x equals 1. Okay, so for other x values, that's going to give us a different list of numbers that are being added up. And so for each of the x values, we're asking ourselves, all right, is this going to be some finite number, or is this going to blow up to infinity? And so we're particularly cared when they approach some finite number, because then this series that we're talking about is a function on those values. All right, so let's first take a look at an x value where this doesn't work. So when x equals 2, what this series looks like is 1 plus, well, 2 plugged in here gives us a 2, plus 2 plugged into x squared gives us a 4, plus 8, plus 16, etc. This thing diverges. Right? And so I want to take a look at the graph and see what that looks like. So for x equals 2, we're adding together 1 plus 2, and this isn't quite to scale, but then this would be a 4, etc. So 1 plus 2 plus 4, etc. So because these numbers are not approaching 0, in fact, they're getting bigger and bigger and bigger, this series, 1 plus 2 plus 4, diverges. So we say that our power series of this original function over here is not defined at x equals 2. In fact, it diverges at x equals 2. What we're interested in, and so, but it converges at x equals 0, we want to know where's the cutoff. What are the values x where this thing actually converges? All right, so that was x equals 2. I want to talk about another one. Let's take a look at x equals 1/2. So when x equals 1/2, algebraically what the sequence looks like is 1 plus 1/2 plus 1/4 plus 1/8, etc. Well, this ends up actually approaching 2, I believe. Yeah, 2 sounds right. Yeah. So this thing converges. So 1/2 is one of those points, x equals 1/2 is one of those points where this function is defined. And so again, I want to take a look at the picture over here. 1/2 is going to be this value of 1 plus this value. And when I say this value, what I'm talking about is the height of this, the y coordinate of that point. So 1 plus 1/2 plus 1/4, etc. And if we talk about the sequence of numbers, we'll say that this sequence is approaching 0. And in fact, it's approaching 0 fast enough for the sum of all these numbers to be some finite number, to only be 2, rather than infinity. Okay, so I want to talk a little bit about why. So with this picture, you might guess that the cutoff is at x equals 1. So for anything less than x equals 1, so for now, let's just say 0 between x, so x between 0 and 1, this thing is going to converge. It also converges for some negative values, but we'll discuss that in a second. And for x equals 1 or bigger, it's going to diverge, right? And that's because, well, for a number of reasons, but the main thing is that this is the cutoff for where this series is going to be decreasing. So when it's less than 1, the series is decreasing. When it's bigger than 1, the sequence is going to be increasing. Okay, so I also wanted to address this question of this value, or of these negative values. So if we plugged in x equals -1/2, well, these things are going to be 1 minus 1/2 plus 1/4 minus 1/8, etc. And depending, there's a couple ways of saying why this converges, but this does end up converging. One of them is the alternating series test. That's probably the easiest. The values of the numbers are getting smaller. The size of them are getting smaller. 1, 1/2, 1/4, etc. And it's alternating signs. Therefore, it converges. Cool. So the numbers that we're adding up over here, it's going to be a 1 plus, this is that 1/4 minus 1/2. So it's alternating 1 minus 1/2 plus 1/4. If we had our third, or our x cubed function in here as well, let me add that in. Look like this. Cool, close enough. With that extra piece in there, we're also going to then be subtracting 1/8. And so it's this magnitude minus this plus this minus this, and sort of alternating back and forth with smaller and smaller pieces. This value, this sum, is going to be zeroing in on something. And then the last one I wanted to talk about was something like x equals -2. And sort of the main reason that this function diverges is because, well, we're going to be sort of swinging wildly back and forth. We're going to be adding together 1 and then subtracting 2 and then adding 8. Sorry, and then adding 4, and then subtracting 8, etc. So I want to take a look at this thing that I showed you last time, which was the GeoGebra model. And it's this same function. So we're still adding 1 plus x squared plus x cubed. And now that the things that we're plotting are the sum of these functions that I drew. So at 1, it's going to stay at 1. We said that at 1/2, it's going to approach 2. So that's the point right here. I believe I can annotate it. So this point is 1/2 2, representing the idea that when you plugged in x equals 1/2, no, screen. When you plug in x equals 1/2 into our series, the series approaches 2. Okay, so the reason I brought this up again is I wanted to talk about what's happening off on the left. For these values less than 1, the sum of these things is going to keep sort of flip-flopping back and forth. And each subsequent term is big enough in magnitude that it's going to cause the entire sum to become either positive or negative, depending on if that term is positive or negative. So this series is going to converge on the interval between -1 and 1. It's going to converge to what the actual function is, this blue line. But outside of that interval, it's going to diverge, either because the numbers are getting unbelievably big, which is the case when things are bigger than 1, or these values are going to be switching back and forth sort of each iteration, which is what happens when x is less than 1. Okay, so like I said, nothing new in this video. I just wanted to recap or take another look at this slightly tricky concept. Hopefully that's helped things a little bit. If you're still iffy on this, even after discussing things in your group, please come to office hours. We can talk about this some more. We can do some more examples. Yeah.